picture that they provide, if you look at the virtual representation side, this side, you'll see that they have modeling and simulation as one of the main components. It's right at the top, but it has all these other things. It has artificial intelligence, first principle predictions, empirical models, and so on and so forth. So there's a whole lot of other things that are supposed to go in that then make it a digital twin. And by the way, I'm quite happy if somebody wants to interrupt and ask. It's your call. So this is this is my vision or our vision of what it might look like when applied to semiconductor manufacturing. As I said before, I'm not a semiconductor manufacturing expert by any means. I only got into semiconductor business about 3 years back, so I'm fairly new. I stole this slide from my startup. They are more into semiconductors than I am, and that's why this looks nice, because I can't make a slide like this on my own. So the physical twin in this case is the wafer itself, and there is the top part of it is what you would normally think of in terms of a bidirectional connection, right? Sensor data and controls, and what is more, or what really makes it a digital twin, is this entire bottom piece, where it's recognizing that this system, the physical twin of interest, is actually a system of systems, in the sense that there are details at multiple length scales. There's information at different length scales or time scales, and they all have to interact. So basically, all your information constructs are all these arrows that are bidirectional arrows that are joining or connecting all these components. So it's really not even just one model. A digital twin like this will be a network of models, a very large network of models that connects all the important pieces. And of course, underlying all this has to be a data pipelines, certain data pipelines that are collecting information. There are multiple process steps that this wafer is going to see. And at each step, it's collecting all kinds of different information. And in addition to that, there's also other sources of data. In order to build these bidirectional mappings, you need data. And the data can come from actual physical observations, or it can come from physics-based models. I'm using the word physics-based models in very broadly. So it could be any modeling and simulation tool, including empirical models, including any domain established rules of any kind. So that's all of them, I'm calling them as physics-based models. Sometimes there is some domain expertise that's beyond these physics-based models. And there could also be legacy data, maybe reports, prior reports, or whatever else. So all of this has to come in to make these bidirectional linkages, which then inform them such a way that we can realize value. Again, remember the word decision making. So the entire target here is to make important and smart decisions on our physical twin of interest. Okay, so now get into meat of what I do, or my group does. We recognize this is a fairly difficult task. I mean, obviously, right? It is an incredibly hard task. So we're asking what is the philosophy? What is the overall direction? How do we go about this? So we recognize that there are many data sources. The data sources are either physics-based models or experiments or expertise, knowledge, etc. But we recognize that all of them are incomplete and uncertain. So in the sense that physics models have their own incompleteness. In other words, there's a famous saying that says all models are wrong, but they are valuable. So in that spirit, physics-based models have certain things that are incomplete about them, and it will always be the same. It will always remain incomplete. In the same way, one could also argue that experiments are also incomplete. Observations are also incomplete because of machine resolution limits, cost, etc. But we have to deal with them with what we have. So the third bullet is really saying, in order to derive maximum value out of this, we need to.
Surya, excuse me.
Sure.
What I'm seeing on the screen, there are bullets, but in very slight gray. And okay, now it is what
I think the
English.
connection is a little bad, so that's why even when I move things, it's not moving
Okay, it's
fast
good.
enough.
Now it's
Now
good.
it's
Now
good.
it's
Okay, sorry. Okay. So the main point of the last bullet, which is the important one, I'm going to stress for the rest of my talk, is the uncertainty quantification and propagation. In order to make smart decisions about our physical twin, our only alternative, given all the incompleteness and uncertainty from all the data sources we have, is to basically be really good at uncertainty quantification and propagation. And again, that's not really a totally new idea, but the opportunity here is that the nature of our problem is very high dimensional. So if you imagine the process steps that I showed you on the previous slide, let's say there are 1,000 steps, then the dimensionality of this problem becomes very, very, very large. And so then the question then is, how does one do this UQ, and UP effectively? And that's where I see an opportunity for AIML. Artificial intelligence and machine learning presents a new tool set that allows this to happen. Without that, the last bullet would be pretty much impossible. And that's where I'm going in this conversation. Because the first two bullets are relatively well established in the domain. So I'm just really focusing on the third one. And now I'm going to switch to material science because after laying out the overall idea, all my examples, everything I've done in my career is centered around materials. So I hope you can make the connections between the materials world I'm showing you and the examples I show you in materials and the semiconductor manufacturing world. As I said, I think the connections are there. I'm not the best expert in that, but I'm looking for collaborations and partnerships with many of you in the audience who can then we can work together, hopefully, to make that connection or make that bridge. That's what I'm hoping for. Okay, so in the material world, the physical twin, it really is just a sample, a small coupon of a
Okay, hold on.
material.
The same thing happens again. Like it's not advancing. I think you have a diagram coming.
Okay,
You're still
it's
on the
kind of
bullets. Yep, the ghost one
uh,
of the material coming.
I see. I see. So,
okay.
how can we?
Now it came.
Now
Yeah,
it came.
works.
Okay. So I think it's just the connection is bad. So I guess the bandwidth is not there. So sorry about that. So I'll slow down and I'll just go. I'll speed up some slides here and there so that we don't lose time. But I'll do what I can. So the physical twin is nothing but a coupon of a material that has some known nominally known chemical composition. The overall composition is known and the overall process history is known to some extent, right? I mean, to the extent it has been documented. Now, if I want to build a digital twin that behaves like that physical twin, no matter what I do to the physical twin, if I do it to my digital twin, I want the digital twin to replicate whatever the physical twin is doing. That's not an easy task, mainly because that piece of coupon of material is already a system of systems because it has way too many details all the way from the atomic scale to the macro scale. And in performance, for example, mechanical properties are largely determined by the defect populations that reside at different length scales. So that defect population is not showing up in the nominally known chemical composition because it's just an average chemical composition and an average process history. We don't know any of the details that are in there, right? So in order to do that, people in material science do a lot of microscopy, a lot of simulations, and try to get clues. And essentially, the digital twin, one can look at digital twin as a task of building a consistent and coherent picture, taking all the different clues from these different bits of information, whether they come from experiments or simulations. Either way, that's a task. So to be able to do that, sorry, okay. To be able to do that, I know the slide is going to take a little longer, so I'm just going to slow down a little. Uh, to be able to do that, you need a statistical framework, a mathematical statistical framework. And essentially, this is a framework that we have developed in our group. And essentially, what you're seeing is the equation. The most important equation is the one at the bottom. And when you see when it shows up, you'll see
It
it.
hasn't shown up.
It has
But
shown up.
Surya, why we're waiting for that? Okay, so that, I mean, it's meant to be a simple example, right? Physical twin, like that little rod, and then, well, you have some experimental data there on the right for the digital twin that informs some form of model, I suppose.
Mhm.
But in this example, like, how would you describe it as a twin in terms of that bidirectional linkage between the physical twin and the digital twin? Just like for us to understand in this case. Maybe it's not
Yeah.
the best example, but how would you control the physical twin
Yeah,
and
no,
how would
it's all
you get the
coming. No,
feedback?
it's all coming, because if I say all
What's
that,
coming?
then the rest of my talk is useless, right? So let's talk through this.
Okay.
And
All right.
then if it's
We're
still
sticking
not
to the
clear,
example.
I'm happy to have a conversation with you separately offline, because otherwise it kind of, my storyline is kind of destroyed, right?
Perfect.
Okay, so let's, anybody who is interested in a longer conversation, please connect with me. I'm more than happy to talk. Okay, so
We're
having
still
said
waiting
that,
for your next slide. Some of your
So yeah,
bandwidth
maybe
might,
can you stop your video? Because if it's
Yeah.
a bandwidth issue, maybe you can stop your video and that will speed up things up. Let's try
Okay.
that.
That's a good idea. Let me see, where do I, okay, I stopped my video. Did it do anything?
No.
I flipped the pages again. I don't know if, yeah,
Oh,
now it came.
Yeah, very
it's
good.
6.
Okay.
We're looking at some definitions.
Yeah.
Mathematical
So,
foundations, digital twins
mathematical
from material
foundations.
samples.
Now, I'm wondering whether I should switch from a presenter view to the other one. Would that be easier? You
Well,
think?
just try, just continue. Go ahead so far. We'll see
Just
how.
continue. Okay. Okay. Okay, so the mathematical foundations are largely statistical in nature. They account for all kinds of uncertainty both in the experiments and in the simulations. And the equation at the very bottom, it says, what is the distribution on the response of a material? If you give me a coupon of material and you say, go predict its response. Response could be, for example, elastic properties, plastic properties, fracture, fatigue, conductivity. It could be anything that is a property of interest. So if you want to know the property of interest, again, in the stochastic world, you cannot deterministically tell you what is that property value. All we can tell you is a distribution, and that distribution accounts for all kinds of uncertainty. And the uncertainty comes from knowing the material itself, because the material structure is controlled by the processing history. So there is some uncertainty in the processing history, but also there is some information from physics-based models when you run DFT calculations, when you run phase field models, because all those models, except the first principle models, rest of them, all of them have fittable parameters. And the fittable parameters one has to estimate them from something. And they have to be, usually they're calibrated to experiments. But that calibration process itself has some uncertainty. So theta in my equations, theta are all those fittable parameters that are fit between simulations and experiments. The uppercase symbols, M, L, K, and phi, are all the observations. These are like, in your world, maybe these are sensor data. These might be basically metrology, all kinds of metrology, right? So the uppercase symbols are all metrology. And so the overall equation is telling you how to compute that, right? It's just a mathematical statement of all the uncertainty. So having said that, I want to point out the opportunity.
May I make a comment about this?
Sure.
This is one of the issues that we normally see, that basically, I guess my question is, how do you fit how do you make the uncertainty to be just stochastic? One of the important things on our side is to really separate between epistemic and aleatoric error, because many times, just because the model doesn't consider something, we say, oh, it's stochastic, but in reality, it's epistemic because we do not consider it. So
I mean, I'm glad that you're talking because I kind of gave this, I prepared the slides at a much lower level than that. I think there is a discrepancy term. To put it shortly, we use a discrepancy term, but I don't have that in this description today. So let's talk offline because that
Okay.
will, right? That's that kind of
Okay. Yeah, that's okay.
great point. But unfortunately, I didn't put that level of detail here. Okay. Instead, what I wanted to point out is where the opportunities are for AIML. The question was a great question. It has to do more with the statistical formulation itself. And instead, what I'm going to do is to identify the opportunities themselves. Why is this a big deal right now? So there are terms in this equation that that need to be evaluated, and some of the terms are very hard to evaluate. So the one that's highlighted in red is essentially what you call as an emulator. In other words, you have a physics-based model, and the physics-based models are computationally expensive. So you want to be able to get the same results or equal quality results as a physics-based model, but you want to get them really fast. With some uncertainty. Obviously, there is some uncertainty. So that kind of fitting is essentially what you would call as a surrogate model or an emulator. And obviously there are many tools. And in fact, this is probably the best known application of AML. Everybody understands this part very easily. In what I'm doing, there are many, many more tools other than the two I showed you on the screen. The ones that we like this because they allow us to do Bayesian stuff, so we can actually do uncertainty quantification along the way. But there are many others, right? I'm not going to talk too much about that. So another set of tools that we use quite a bit is dimensionality reduction, because quite a lot of the sensor data is very high dimensional, and essentially you need some sort of dimensionality reduction. And on the axis there, I'm showing you a variety of dimensionality reduction algorithms that are available, mostly because of, and they're all different methods within AML. And these packages now are readily available. And most of these packages are readily available. And essentially on one end is PCA, which is, in my mind, at least the most interpretable one. And the other end is the variational autoencoders, which
Surya,
is,
I'm sorry to interrupt you. I think you're not in the right slide. This is Ganesh. Hi.
It's slide number 7 now.
I'm on slide 8. Okay.
Okay.
Oh, we need to wait. Now, okay.
Now it's wait. Now it's wait.
Now
Whatever
it's
you
8.
did,
Yeah.
that's how you advance. Yeah.
Okay. Sorry. I think, yeah. So sorry about that. So there is a dimensionality reduction there. And so there are multiple choices there, all the way from PCA at one end to VAE at the other end. The difference really is expressivity versus interpretability. Right? On the left is more interpretable, on the right is more expressive. So the expressive meaning that we can pretty much do anything. On the right, towards the right is pretty much universality. You can do anything you want.
Okay, sorry. So PCA is principal component analysis. What is VAE?
VAE is a variational autoencoder.
I see. Okay, thank you.
Okay. Now I'm on slide 9.
You were briefly. Now
you were with slide 9, but you get back to.
I went back because when somebody asked a question, I went back, but I came back to slide 9.
Oh, that's the latency. Okay.
Okay, that's the latency. Sorry about that. So I'll slow down and see. I think hopefully you can see slide 9 now. And so the second, another term that's very...
Not yet. Try to click one more, perhaps.
No, because if I click, it'll go back to slide 10. So might as well just wait.
Right?
Okay. So Surya, since we're looking at that in the equation, right? There is like a term under the integral, the very last distribution. Like this is just a notational question. Okay, so on the left-hand side of the equation, you have a distribution. Then the last term under the integral, it looks like the same distribution, or is that a different distribution?
Like the last one and which one? The last one is P theta given LMK phi. Is that the one?
Yeah, and like, is that the same as what is on the left-hand side, which is P as function of K given LW, K, and phi?
No, so K is the response of the property, material property of interest, right? So K and theta are different.
Okay.
So
They're different distributions. Okay, got it.
yeah,
It's
they're
just like a
completely
notation.
yeah.
Got
Okay. Okay. Can you see slide 9, or
No.
are we still? Oh my God, that's so. I'll go. Should I
Okay,
go
now
up?
it's 9. It's 9.
It's 9. Okay, that was way too long. Maybe everybody can turn their videos down. I don't know if that helps.
We can. I don't think. I mean,
Anybody
it
is
matters
else?
on our side, but
Uh,
we can try.
Oh, you think it's on my side? I see. That's interesting. I can move to a different place and see if it helps. Okay. Okay. I'll try. I'm trying to do it from a different place now.
Are you at Georgia Tech?
No, I'm at home today.
Oh,
Yeah. Sorry. I probably should have gone there. So let's see what happens. I move to a different place. Hopefully, it'll get better. So the one other area that is hard is the basically inference. So, for example, the term in red at the top is where you're matching the experiments and simulations. So one of the hard areas is how do you match experiments and simulations. So normally people would call it model calibration, and mostly people, in the most simplest case, the most common approach to this is a deterministic matching. So you define an objective function and you minimize, right, the difference between the experimental observation and the simulations. And so oftentimes there is identifiability issues in that, in the sense that if the number of parameters is large, the solutions, the matching solution, the calibration is not unique. There are multiple combinations that might fit the same experiments. And so one has to then do this, a better way, a more formal way is to do this in the Bayesian inference. And that essentially uses Bayes' theorem, which is based on a prior and then a likelihood and a posterior. And the surrogate models, the emulators, which I talked about in the previous slide, are very helpful to compute the likelihood, right? And so doing this way, you actually get to quantify the uncertainty involved, and you're able to propagate it through your system. So now I move to slide 10, and essentially this has to do more with optimization. In fact, I'm going to skip this slide because we will be running out of time. And I'll talk about, and I'm going to skip a couple of slides, and I'm going to slide 12. In the meantime, I'll talk about it, because from here onwards, I'm showing you how these tools are used, because I think you get a sense of this, of the available statistical tools today because of AML. There are optimization tools, and then there is also Gen AI. Again, when I say Gen AI, I don't mean large language models. I'm actually talking about inverse problems. There is a new way to solve engineering problems or inverse solutions in engineering using Gen AI, which is essentially coming up with a conditional probability distribution. That's what the underlying math is, right? So I'm going to skip those details given where we are. But if anyone is interested, I'm more than happy to have a long discussion. So now I'm on slide 12. From here on, I'm just going to show you some examples of where we applied these tools and we're able to do things that were previously not possible.
I
Right?
think we're still on 11.
You're on 11? Okay.
Like on the AI ML2 Bayesian inverse for design.
Inverse, okay. So I'll leave it on slide 12, but I'll talk about 11 just so that we have something. But as soon as slide 12 comes up, let me know. Please let me know. And essentially, the Bayesian inverse. So when you do inverse problems, almost all inverse problems are ill-posed, because in the forward direction, one input has one output. But in the inverse direction, if you specify an output in many of our problems, the number of inputs that might correspond to the output could be many, because many of our connections are many to one. So in the inverse direction, what one really needs is an opportunity to explore the entire input domain or input space. And essentially, these kind of ideas that the two slides I jumped over or tried to jump over give you an opportunity to explore very large input large dimensional and large dimension input spaces and give you solutions. So in one step, in Gen AI is very good at cutting down the space of design space down to something much smaller. And then within the smaller space, you can do Bayesian optimization to get to that particular one that you have an interest in, right? So with that, I hope you can see slide 12. Are you
Nope.
able to see? Not yet?
Not me.
Okay. Okay. Because then I was going to focus on examples.
So okay, that's all good. But this generative AI you said is not LLM. So then what is it?
The underlying math of LLM is generative AI. So when people talk about generative AI, they're talking about a method to come up with a conditional probability or a joint probability, right? It's a probability distribution. The underlying math is about how do you compute this distribution. In LLMs, they use this idea to say, if you prompt me 3 words in a sentence, what is my 4th word? They use that math tool to do that.
Mm-hmm.
But you don't have to restrict yourself to predicting what the next word in language is. You could do the same thing in terms of all kinds of engineering problems, right? Suppose you want to design something, you can actually think of applying the same math where you're saying, I know these parts, but I don't know the other parts. So given this, what is the conditional probabilities for the ones I don't know? That would again be a Gen AI algorithm.
Okay.
Okay.
Can you like flip something one more time? I'm not sure if it just gets stuck. Like we're still on the page 11, I think.
Okay.
Oh, now it
yeah.
can.
Now it.
Which one? Which one do you guys see? 12 or 13?
Synthetic data generators.
Okay. So I'm actually on the next one. So maybe it's always one behind me. I don't understand that. But anyway, so I'll talk through it. And if it changes to the next one, it's because I'm on 13. So on the data generators, this is one example of Gen AI where the one picture in each case, there are 2 examples there. In each example, one picture is a real one and the others are completely synthetically generated. But they reflect the same statistics, some same higher order statistics. There are statistics that are extracted, and we can convince ourselves that, in other words, the synthetically generated ones are basically the digital twins of the original one, right? So they are similar. They're not exactly one to one, but in materials world they are similar because they have the same statistics. So they're expected to have the same properties and things like so. So what is interesting there is that these are fairly complicated in terms of the information content. The picture in the color has what are called as Euler angles. At each pixel you have Euler angles, and it's capturing the spatial distribution of these colored features, because you can see some of them are long, some of them are short, so on and so forth. And the picture on the right has only 4 states. There are 4 different colors, but the shapes and size distributions of each one are different. And what is happening in the replicators, or the ones that are generated, they have very similar statistics, both in terms of shape, size, and separation and distribution, and so on and so forth, right? So that's an example of what can be done. The next pictures, I don't know if you got to the next one.
Yeah, we see it. Case studies.
Case studies. So it looks like I have to be always one step ahead of you. Okay, so now I got the idea. So I'm going to. So the case studies are examples of applying these emulators. So in each case there is a physics-based model, a fairly sophisticated, expensive physics-based model. And what I'm showing there is that there's a general framework in which I can apply to all kinds of different physics-based models. Some of these models have to do with flow, permeability. Some of them have to do with mechanics. Some of them have to do with electrical short circuit properties. It doesn't matter what the properties are. Pretty much the same general framework is able to produce emulators for all of them. With that, I'm going to give you, moving to the next one. Yeah, I think now I finally figured out how to do this. Sorry about that, guys. Uh, so here is an example in DFT computations where we are doing similar things. We are taking the charge density field and we are predicting properties, bulk modulus, for a quaternary system. It has 4 atomic elements. And if you think of all the different compositions I can make up with 4 atoms, 4 elemental compositions, the list is incredibly large, right? The number of possible designs is incredibly large. And what is shown there is that we can build an effective, because of these tools I'm showing you, we can build an effective model with as small as 10 DFT computations. That's all we need. At least for this property, that's all you need. After that, the increment in value, or what I'm learning more after 10 increments, is rather small. In other words, I might as well go try something else if I want to learn more. There's not much of a value there, right? So then in terms of matching experiments and simulations, what you're seeing in the slide 15 is there are, this has to do with hypersonics, damage evolution in hypersonics. And essentially, there is very limited data. There's very little experimental data. There are only about 7 experimental curves there. The models are much more sophisticated. They have way too many parameters that are unknown. And essentially, what I'm showing you here is that the Bayesian approach actually does a pretty good job, even with taking the limited data. It's able to produce estimates for the different parameters. If you look closely, you'll see that some parameters are not well estimated. Particularly, there's one, I think it's called H or something. And you'll see that it's not doing a good job there, but it's saying that within this data set, there's not enough information to give you a better posterior on that particular variable. But the other advantage of doing something like this is in the in the bottom picture on the right, there is a map and it's saying where is the next best opportunity in terms of doing experiments. So if you're going to do one more experiment, where should you do it? And there's a yellow dot that shows where there's the highest potential for information gain or a new acquisition of knowledge. And that's what is guided. So again, decision making is where all of this is aimed at. And the just like you think of systematically guiding what is the next experiment, you can also use the same tool set to guide what is the next simulation. So in slide 17, what you're seeing is a bunch of models that people have published in literature for the same problem. But everybody claims, if you read the papers, they'll all say that this is the best model. But of course, there has to be an arbitration. Somebody has to show which one is really good. And essentially, what we are showing is the tools I presented are capable of computing what are called as relative model probabilities. So you can actually objectively compare models because the models have different number of calibration parameters. So you have to objectively calibrate the parameters and then figure out what is more likely to be right. Oftentimes, the answer is not that something is really bad and something is really good. You will actually get maps of the kind that are on the top right that show that a particular model might be good in some regions, another model might be good in another region. And therefore, the opportunity that an analysis like this shows is what are the features you might want to combine to make a new model? What should your next model be? So after all the given models, what are the best pieces of each model that I want to combine and produce a new model? So again, decision making and support, right? And the last example I want to talk to you about is this inverse problems. So in material science, we talk about process to structure and structure to properties. That's on slide 18 now. I hope you'll see slide 18. And essentially, as I said before, many of these connections are many to one. The opportunity that these tool sets bring you is there is a rigorous way to map back the entire solutions for a given set of targets. So in the picture on the bottom right, there are 5 parameters, the 5 properties. 3 of them are mechanical, and I think 2 of them are conductivity properties. So we are saying there's a black line right in the middle. I hope you can see that. And though that is a particular combination of properties we are assuming we are interested in. The black line is the actual properties of interest. The combination properties of interest. Using these methods, then we're able to map back to the middle set of micro. So each square in the middle set is a possible material structure that it's a composite. It's made up of different components, phases that are arranged in different ways. So we're able to map back to the material structures that are potentially going to give this 5 combination of properties. And from there, we're able to map back to process history, which is on the bottom left. There are 3 process parameters that are controlling this microstructure. So we're able to map back to process history. But when you get into the process space, what you see is that there are many combinations of process. There are 3 process variables, so it's a 3-dimensional distribution. What I'm showing you are projections, obviously, but it's really a 3-dimensional distribution. But you can see that many combinations are able to match the target. And so in almost like a closed loop, what you then do is we sample this 3-dimensional distribution. We take the process parameters in the 3-dimensional distribution and then move back or push them back into microstructures. But this time we use the real physics-based model. So in the inverse direction, we are using physics-based models, which is ground in some sense. For this toy example, the physics-based model is a ground truth. And then from the structures, we go with finite element models, we go and predict the properties, again as ground truth. And what you're seeing are the distributions now. So the targets are the black lines in the bottom right, and the distributions are what comes in the return loop, in the loop that coming back. Basically, what it is saying is we are able to connect the target, the output, the 5-dimensional, a point in the 5-dimensional space to a fairly large set of points in the 3-dimensional process space, and we are able to come back and see that it does a good job, right? So that's the last example, and with that, I'm going to let you see the summary statements. Essentially, I'm trying to show that there is enough here in terms of tool sets that are able to address these problems in a more fundamental way. Since I can't see the last slide because I need to always push in front of you for some reason, I'll leave it on there and I'll let you read and take any questions.
Yeah, Surya, just for information, we see just black slide, end of slideshow.
Is that
so? Okay,
that better?
now
there it is.
now
okay.
now it's
now actually I can see the same slide as you guys. Then that's strange.
Okay.
I don't know what's totally wrong. Something is I don't know. I'm sorry. I probably
Well, I mean,
You're good. It's all good.
yeah, good. Teams can be tricky sometimes. I experience similar things, so don't worry. But let's just see the summary statements, and we already have questions.
Yes,
Ganesh, you are first.
So yeah, very nice talk. Very good to hear the UQ side of the digital twins. Can you go back to the last slide, the 18th slide, not 19th, but 18?
Okay. Can you see it now?
Not yet.
Okay, I moved back.
Okay, maybe I can explain verbally because we're not seeing the slide yet.
Okay.
Actually, if you get out of slideshow and just, I don't know if you're using PowerPoint, but get out of slideshow.
It's 18.
I don't know how you're doing this.
So the structure property relationship, I think you were...
We don't see slides at all, please.
You don't see slides at all.
You stop sharing. Stop sharing.
Okay. So
we see it. Stay where you are. Don't
now
do
you see. Now you see the present the slides, right? Not this show version, but the actual slides. Correct?
We see. We can see.
Yeah. I think that's what I should have done because this. Anyway, go ahead, Ganesh. Sorry.
No problem. So again, nice talk. I think the structure property relationships, the physical models are very well, I would say more or less well understood in mechanical behavior. But what we are trying to do in semiconductor manufacturing is to connect structure to yield or reliability. Those tend to be prominent quantities, output quantities, and process to structure, structure to yield or reliability is what we are trying to connect. And unfortunately, the question marks that you have exist both ways. The physical models themselves are not very well understood.
Okay.
So,
So Ganesh, just not to interrupt you, but even in material side, the forward ones are not well established. So I mean, for some simple properties maybe, but for most properties of interest, they're not well established at all.
true, fair enough. But I think let's say they're better defined than in semiconductor processing.
Okay, okay, okay.
So what would be the steps that we would have to go through in order, for instance, let's say I want to tighten manufacturing yield. I want to get it to, or reliability to say, 6 sigma and 3 parts per million type failure mechanism. What would be the steps that one would typically have to go through? I think that would be very helpful based on your experience.
Good. No, I mean, obviously these are great questions, and definitely we need a longer conversation time. Happy to talk to you anytime. We can set this up. They basically from an AI/ML perspective, right? There's no magic anywhere. Answers have to come from data. Only difference is there are different data sources which different data sources have different capabilities. So the remark you made about materials versus semiconductor, in my mind, what it translates to is that in different data sources, in some data sources are more reliable and some data sources are less reliable. Whether it's an experiment or physics-based model, it's still a data source for us. And what we're really talking about is to learn. There's no chance in any of these problems that one data source is so good that it provides all the answers, because the one that provides the good answers might actually be very expensive. So you can only use it like 3 or 4 times maybe, right, budget wise. Or the one that is cheaper, you may be able to use thousands of times, but it is more uncertain. But there is still value in there. So essentially, the framework is all about trying to give you guidance on at any point. So the question that we are formulating is, at any point in this development cycle, you're saying, these are my data sources. This is what I know about these data sources. Which one should I try and use? Which one is likely to get me where I want? Right?
So you would say that, just to continue this discussion, you would say that any data source is valid, go after all of them.
Yeah, I mean, any data source is valid. Learn about the data source enough so that you can actually model the data source. So in some sense, we are modeling the data source. We're saying, is that the right data source for my next step? For me to produce, if in my semiconductor processing, if I want to increase my yield, what is the right data source that is going to get me there? And which one do I need to pay attention to? Which one do I need to tweak more?
Okay, thank you.
Okay.
Thank you. We have so many questions. So Henning is the next. Henning, and next is Bhagat.
Yeah, so it goes back to your original or the National Academy's definition of the digital twins. I mean, in my mind, clearly you focus on the forward information flow, establishing the physical twin and making sure it corresponds to the physical data. I think that is actually the hard part and the very important part. But could you give some kind of example how the loop would be closed? Basically the feedback back to the physical twin, maybe the decision making or any kind of thing you would do to control the physical counterpart.
Right. So what I'm trying to say, and again, I'm sorry if the story is not coming through carefully, but please feel free to connect with me, and I'm more than happy to go through this. What you're talking about, the forward are the blue lines. That's what happens in physics-based modeling and so on and so forth. But in this picture or in this example, I'm trying to show that in the inverse direction, I want to control. Through the controls, I want to change something in my process, right? The process variables are the ones that I'm able to control in some way. So I'm able to say, if I target, if in a process my target is somewhere else and I want to move my target, then I'm able to use this machinery to be able to look for where the options are and do it relatively fast.
I mean, essentially, you would do the inverse modeling, determine how you need to change the knobs of the process, and then I guess you will say trivially, well, in practice, well, we will just change those knobs, and then that close the loop.
And it may happen in especially in an R&D environment. This is going to happen in loops, like you say, but usually the target here is to minimize the number of loops. So we are not saying this is going to happen in one loop, essentially, right? Because it's impossible. The problems are so complicated. That's why the dynamic part is also somewhat important. And what we're saying is our target is to minimize the number of trials to get there.
Yeah. And Henning, just to add to this, I think your questions refers to slide 2 or something, where there was a piece of material compared. Oh, next, whatever, piece of material versus model, something on. Yeah, this
definition of digital twin, right?
It was initially a physical twin. So yesterday you gave a very good example. For example, reliability tests. So there are 1,000 physical components, and we trying to break them all, right, in accelerated testing or something. And the question is, can we break it or not? And it is already closed loop to me. So you don't need to go back to material. You just have a material, and instead of breaking it physically, you break it in model, right? Or test it in the model. Provide accelerated.
No, you have, like, physical is physical, right? You have to go back to the real world.
Yeah, but this means you throw it out or use in your product. It is the thing. The loop is still closed.
So that would be the decision making. It's kind of more of a higher level.
I mean, maybe in some cases, right? You do a one-time decision and you can never go back. But this is more about iterative decision making, right? So.
It is iterative decision making. Exactly, it is. Good, thank you. We need to move on. Bhagat.
Well, I just wanted to tell you I really enjoyed your talk. It was excellent, and I learned a lot from it. Thank you. The only other thing I'd like to add is that with digital twinning, sometimes the system behavior, even though it is well described mathematically, can be chaotic. And under these circumstances, I think we need to recognize that it's not predictable, and a digital twin can exist, but it will be equally chaotic.
Yeah, I mean, again, the way I say it is there's no magic anywhere. We want to be as rational as possible. And I think the way I look at it is AML, beyond being the universal interpolator that everybody is using it as, it is an amazing interpolator, but it also has these other applications where we can do certain we can look at design of very high dimensional design with sparse data sets. It provides another opportunity to get into that field, because in that particular application, there are really no other way to do this. As far as I know, there's no other way to do this.
Thank you.
Yeah, thank you. Saurabh?
Hi, Surya. Thank you for the talk. I had a question. When you compare the models, there was some probability involved.
Yes.
I just want to clarify, is there a need for experimental data to compare the probabilities, or is this all computational?
No, this is, so the way it is posed is there is a limited amount of, there is a certain amount of what we call as high throughput data, because when the models are complex, you need as much data as you can get. And data is very expensive in these cases. Yeah. So in this particular case, we happen to have a limited set of high throughput data. So these are not standard tests. These are non-standard tests. This one came from spherical indentation. And essentially, we are able to say that for this grain level, all of them are colony models, lamellar colony models, all of them, models 1.1 to 2.5. They're all in literature, from literature. None of them is our model, so we don't have any bias. And we are able to, using that consistent one experimental data set, we're able to say these models win. But the ones that lose are not useless either. They actually have features that are useful. And the one that lose if those features from the ones that lost can be incorporated into the ones that win, then you get your next generation model. And we have shown some of the references there, we have shown that that's actually possible to do.
Okay, thank you.
Thank
Shankar.
you.
Shankar? Sadas?
Yeah. Thanks, Victor. I didn't know whether you were calling out me or someone else. Sorry.
Yeah, I'm sorry.
Okay. So thanks for a very nice framing of the problem. I had a question on any specific experimental validation. If you take a small subset of what you showed, take a structure and a property, is there anything that was done in terms of Bayesian model that cannot be done in terms of a correlation of experimental data?
So, I mean, everything is a correlation, but the answer is that the correlation is not one set of correlations, right? So in this case, there are, for example, in this case, these are the experiments, this is the model, right? But essentially, if you look at some of the variables, you have a very nice distribution. It's narrow enough. It's still not deterministic, right? None of these are delta functions. A delta function would be unique value, essentially, right? None of the distributions are a delta function, but some of the distributions are pretty broad, right? For example, this one is saying that for this particular experimental data set, for that particular model, it's going to be very hard to establish this value because it's kind of very broad. You can see it's very broad, right? But nevertheless, if you go back and you fit the parameters in a Bayesian framework or a probabilistic framework, and then you say, what are all the possible curves that could have been measured? So all the blue lines are the possible measurements that could have been made from the sample based on the model. The black line is where the actual measurement was done.
Yeah, I can't separate the black from the blue. Okay, I'll take your word for it.
So yeah, I think I'll make this PDF available so you can look through that. And all of them have, most of them, or at least have these references. You can actually see the original data in the references. But if you look through that, it's not so bad. I mean, obviously there is one experiment here where the curve, the experimental curve is so far away from the model. But what the Bayesian stuff is saying is that this is the best you can do. Given the data, this is the best you can do for that model, right? Again.
Thanks for that detailed explanation. I was asking for something much simpler.
Oh, okay, sorry.
Any experimental prediction that came out of this model that was subsequently measured and found out that it actually did something. I'm trying to look at it from an industrial perspective, because that's more like a bottom line question.
I mean, in academic exercises, I think what you're describing is what we would call as an inverse solution in some sense. And then you're asking if the inverse solutions are validated. I think I have academic papers where we make up these problems because we don't own problems, right? We don't have any engineering problems, real problems, unfortunately, right? So we make up the problems, we pretend that we don't know what it is, and then show, look, I predicted what it is. I don't think you're going to be impressed on that based on industry, but you know, this is where I think the opportunities are. In some sense, we have the tools. Industry has the problems. We would love an opportunity to connect the two.
Okay, thank you.
In some sense, you know, that's the opportunity, I think.
Okay, thank you.
Yeah, by ourselves, we always make up these problems and prove to ourselves that things are right, at least, right? But
thank you so much.
Sure.
Thank you very much, Surya. It was great talk, and